Hello everyone, welcome to the class once again. I hope you all enjoyed the last classes in this chapter, and now we'll be taking the last topic today. In the last class I was talking about heat engines. I developed the equation for heat engine, its efficiency. Today we'll go ahead and we'll understand the refrigerator concept. Before that, let me tell you about Carnot's theorem. Now Carnot's theorem states that for any kind of engine, its efficiency cannot be more than the efficiency of a Carnot engine that already we have studied, that is working between two temperatures. So I will state that the efficiency of any engine, the efficiency of any heat engine cannot be any heat engine working between two temperatures. I already have told you that any engine will be working between two temperature sets. So any heat engine working between two temperatures, cannot be more than Carnot's idle engine. Cannot be more than an idle Carnot's engine that already I have discussed in the last class. Cannot be more than idle Carnot engine. Now efficiency of Carnot engine I have already discussed in the last class. It was actually work done with respect to the heat supplied. This was what I have told you in the last class, and then we have also derived for various processes, the various steps that the gas takes place while taking the heat from one body to and doing some work and then releasing all the leftover heat to the sink. Now today we will be learning the next concept. The next concept, that is the refrigerator. In the last class we have talked about heat engine. It was taking heat from some object, some source, and then it was utilizing some amount of heat to do some work. And then some amount of heat was rejected to the sink. That is what we have studied in the last class. Today we will see the reverse process. You all must have used refrigerator in your house where you keep the things to let it coolify. How does that work? Have you ever imagined that the inner temperature of the refrigerator is quite cool compared to the external temperature? What that refrigerator is doing? It's taking the amount of heat energy from the interior of the refrigerator and releasing it to the outer atmosphere. So you must be thinking that it is disobeying the natural law. We know that from natural law, heat energy can be only transmitted from a body at higher temperature to a body at lower temperature. But what is happening here? Heat energy is transmitted from a body at lower temperature to a body at higher temperature. That is what we observe in the working of refrigerator. How does it work? You see that we all know that a compressor actually does work on the refrigerator to coolify interior. Now before that, let me just give you a quick recap of what we have done in the heat engine. In the heat engine case, what we had a source at a particular temperature. Let's say the temperature is T1. It supplied certain amount of heat to a working substance. You must be knowing about working substance, that is the gaseous system that we have taken. This working substance, what it did some amount of work, and then it rejected some amount of heat energy to the sink. This is what we have learned in the last class. Now the amount of work done that we have observed, that was Q1 minus Q2. You can see the balance. This amount of heat energy that was taken from the source, that is Q1. From Q1, Q2 amount is rejected, and the leftover released, that is Q1 minus Q2, this is taken as the work done. This much is the amount of work done. This is utilized in running the machine. Just reverse of this is we will be having the refrigerator. Let me talk about refrigerator. We all know that how refrigerator works. Refrigerator will take some amount of heat energy from a body at lower temperature, and then the compressor will do some work on the working substance, and then some amount of heat energy will be rejected to the external surrounding. Let me show you the reverse way. Suppose we have, this is the actually from where the heat energy has to be taken. So let me take this as sink was here. from where, now this is the place from where heat energy will be taken. So let me go ahead and let me mark here that we are going, and let's say this is the heat absorber. Or if you can go ahead with the sink, it will be sink also be the more better one, more better term, because we have the sink here to which heat is rejected. So let us go ahead with the sink term, that will be far better. Heat absorber, that is not suiting to this term. So let's use sink. Now from sink you are taking some amount of heat energy Q2. Q2 amount of heat is taken. There is a working substance. There is a working substance which actually on it work has to be done. On it work has to be done, and it will reject Q1 amount of heat energy to the external surrounding. Q1 amount of heat energy to the external surrounding. I am just moving out of this diagram, just take it that it's external surrounding, Q1 amount of heat is rejected. Now that means the amount of work that has to be done on it, that would be Q1 minus Q2, just opposite of the heat engine, sorry. This much will be the work done on the working substance by the compressor. We all know that compressor is actually in the refrigerator that does the work on the working substance. We can see that from the sink, Q2 amount is taken over by the working substance. It will release Q1 amount of heat energy to the external surrounding, and we can see that the amount of work done from here, that will be Q1 minus Q2. Easily you can absorb. You can easily observe that as I have written here. So what do you take note till here? I'll start from the other end. So I believe that you have understood the relation between both, that what is how refrigerator works and how a heat engine works. Clearly you can identify that both work just opposite to each other. Heat engine will just take some amount of heat energy, it will do some mechanical work, and then it will release some amount of heat energy. This working of the heat engine actually transmits the work to the external pistons, which will actually move and which will actually move the cycles of the engine. Now here we talk about refrigerator, we want to actually keep the temperature lower than the external temperature. Already we have a sink, the temperature is low here. Let us say that its temperature is T2, and let's say the external surrounding, external source, you can say that temperature is T1. You are by compressors doing some work Q1 minus Q2 on the working substance, and Q1 amount of heat is rejected. Remember that Q1 is more than Q2. As I have already told you, just I have made the diagram just reverse of what I have made in the case of heat engine. Now let's talk about this refrigerator's efficiency, because that is the most important point for the efficiency of the refrigerator. Let's go ahead and let's write down the efficiency of refrigerator. We do not need this. Now you all must be knowing that efficiency can be clearly identified as, because what is the work that it is doing? It is extracting Q2 amount of heat energy. And what is the work done on it? The work done is Q1 minus Q2. So Q1 has got no role to play, the amount of heat rejected. You see here efficiency of refrigerator. Efficiency we talk about, it is the ratio of amount of heat energy released or extracted from the sink. It is the ratio of amount of heat energy taken away, from sink with respect to, work done on the refrigerator, with respect to work done on the refrigerator, with respect to work done, that was Q1 minus Q2, because this is the ideal way to actually define the efficiency with respect to work done on refrigerator. Now very easily we can give the efficiency of this. Now see, we know that efficiency can be given as, if this is beta, beta will be, now see, the amount of heat taken from this sink, that is Q2. The work done, that is Q1 minus Q2. Clearly you can see this relation. Q2 upon Q1 minus Q2, this will be the efficiency speaking ideally. I believe that you must have watched the last class and was remembering the relation between the ratio of Q1 and Q2 and T1 and T2. In the last class, I have talked about, if you remember the relation, I have said that we have also derived it. I have done the derivation, hope you have watched it. I have said that T1 by T2 is equal to Q1 by Q2. This is what we have already derived in the case of heat engine. The same will be applicable in the case of refrigerator. It is just a reverse process. Now you see here, already I have written the efficiency beta is equal to Q2 upon Q1 minus Q2. So if I divide the numerator and denominator both by Q2, we will be having 1 upon Q1 by Q2 minus 1. This is a term that we'll be having. Now after this we'll be having 1 upon Q1 by Q2 is T1 by T2, T1 by T2 minus 1. This will turn out to be, take T2 as the LCM, T2 will move to the numerator. This is the term you are going to have, T2 upon T1 minus T2. That is, the efficiency will only depend upon the temperature of both the sink and the external surrounding to which the heat is rejected. So efficiency we can write in more easy term, beta will be equal to T2 divided by T1 minus T2. This formula you all remember. This is the only thing that we need to do in the case of refrigerator. The entire derivation of the gaseous cycle is not required in this. That is already we have done in the case of heat engine. And clearly you can see that either if you are provided with the heat energy taken and heat energy that is released, so you can use this formula, or you can use this formula if the temperature of sink and external surrounding is given, you can evaluate the value of efficiency. Let's go ahead, already we have learned this formula. Let's go ahead and let's try and practice one simple numerical based upon this simple formula. Now at your home, let's say you have a deep freezer and let's say you have a refrigerator. So I'm going to give two things. We are having a refrigerator and let's see that which is having more efficiency, and we are having a deep freezer. Both will be working under two temperature conditions. Let's say the refrigerator works under a condition it is actually working to release some amount of heat energy between two temperatures. The two temperatures are given as T2, that is cooler one, from minus 10 degrees Celsius, and it is releasing heat to the surrounding. Let's say T1 is, let's say keep it as 27 degrees Celsius. So we have T2 as minus 10 degrees Celsius, that it is actually working between two temperature range T2 and T1. It is taking some amount of heat energy at temperature T2, that is minus 10 degrees Celsius, and releasing some amount of heat energy to the external surrounding, that is 27 degrees Celsius. For deep freezer, it's given that the value of T2 is equal to, let's say, minus 27 degrees Celsius, and T1 is given as 17 degrees Celsius. So both are working under two different set of temperature conditions, and let's say they are actually extracting 2000 joule of heat energy. This is the amount of heat energy released to the external surrounding, that is actually 2000 joule. Now suppose it is asked, compare the efficiency of both the refrigerator, that is A, and deep freezer, that is B. If it is asked compare the efficiency, so easily we can solve this. Already you are having the formula. You are having the formula of each of the refrigerator and deep freezer. Formula we have for the efficiency. You see minus 10 degrees Celsius for refrigerator. If I talk about, for refrigerator, the temperature T2, we have minus 10 degrees Celsius can be written as 263 Kelvin, because whatever calculation you are required to do, you do it in terms of Kelvin. Keep the temperature in terms of Kelvin. Next, T1 we will be having, that is minus 10 degrees Celsius was the T2, T1 is 27 degrees Celsius. That will turn out to be 300 Kelvin. Next, for deep freezer, I believe that you all must be easily, let's keep it as T2 dash instead of T1 and T2, let's keep it as T2 dash, then we can separate minus 27 degrees Celsius. If I point it out, so 273 minus 27, that will give us 13 minus 7 will give you 6, I believe so 6, and then 6 minus 2, 4, 246 Kelvin, and T1 dash, that was actually 17 degrees Celsius, that will turn out to be 17 degrees Celsius. So 273 plus 17, that will be 290 Kelvin. So I have given you the temperature range between which they are working. The formula for efficiency, that is T2 upon T1 minus T2. Now we do not need this, T2 upon T1 minus T2. So efficiency of refrigerator, that will be T2 divided by T1 minus T2. So that will turn out to be, T2 you see was 263 divided by, we have 300, T1 as 300 minus, we are having T2, that is again 263. So that will turn out to be 263 divided by 300 minus 263, that will turn out to be 263 upon 37. Clearly you can easily evaluate its value. It will be somewhere around 7, I believe so, because you can see that 37, and if you do that, it will be somewhere around 7 it will come. So I am writing somewhere around 7. I am not using the exact calculation, that you can check. I am just giving you an example how to do such kind of question. Now for deep freezer, DF I am writing, for the deep freezer we have again T2 dash divided by T1 dash minus T2 dash. We will be having T2 dash as 246 Kelvin, T1 dash is 290 minus T2 dash again 246. Clearly you can solve it, it will not be a problem for you all to resolve this, and I believe that we have done it correct. Minus 27 degrees Celsius will be 272, 253, yes, it's 246 Kelvin only. So let's go ahead and solve it. We will be having 246, 290 minus 246, that will be 44, somewhere around 44, that will give you somewhere 5 point something, because 44 into 5 will be 220, then we will be having 26. So somewhere around 5.5, I am writing somewhere around 5.5. This is just approximate values I have given you for the efficiency. You can check the exact value while calculating on your own. Now you can see that the refrigerator has got more efficiency compared to the deep freezer, working at two different set of temperatures. Although you must be thinking that the deep freezer is releasing heat energy from a temperature that is minus 27 degrees Celsius. That is far lower than temperature, the lowest temperature for refrigerator, that is minus 10 degrees Celsius. Then to the refrigerator has more efficiency. If you see that it is releasing heat energy at 27 degrees Celsius. The higher, the external environment, the external surrounding has a temperature 27 degrees Celsius. If we compare the difference in temperature of both T1 and T2, I have already mentioned here. You see it's 37 here and it's 44 here. Although you see that the temperature difference that it has to work upon, that is 37 and this is 44, but still we can see that the refrigerator has got more efficiency. The refrigerator has more efficiency compared to the deep freezer. So don't go ahead, what is the temperature, maximum temperature difference exists between the external surrounding and the sink. You must be thinking that that would be giving you more efficiency. No, don't go upon that. You have to solve each stepwise. You have to solve for each and see that although the refrigerator is working at low temperature difference compared to the deep freezer which is working for higher temperature difference, still we are having that the efficiency of the refrigerator is more, because it's releasing the heat energy at a higher temperature at 300 Kelvin compared to the heat energy that is released for this, that is the deep freezer working for 17 degrees Celsius. So I believe that both the classes, the last class about the heat engine and this class about the refrigerator, all your concepts about heat engine and refrigerator would be pretty much clear. What you can do after this class, you can practice questions on heat engine and refrigerators. As I advised you after the heat engine class, that do revise this class, do revise the derivation, the entire derivation that I have done for the gaseous process. It was going through adiabatic process, isothermal process. do revise that, because if you don't revise that, you'll forget each step that has actually been gone through, each process that the gas has taken to reach to the final state. Then you'll find that how adiabatic equations we have made for work, for find the work, for isothermal cases, how for work equation, how we have framed. Then how we have found a relation between T1 by T2 is equal to Q1 by Q2. Still, if you do that, and finally you have to remember the formula for efficiency of both the heat engine and Carnot's engine, for the refrigerator. I hope that all these classes of this chapter will be very much useful for you all. Do revise and do practice more questions. I'll meet you all in the practice exercise for JEE Main Advanced and NEET questions as per your preparation. So thank you everyone. I'll meet you on the next class. Wish you all the very best.